In this video, we will talk about polynomial functions of higher degree and how to graph them. Let's begin. All polynomial functions have two features in common. First is that the functions are continuous. In other words, they have no breaks, holes, or gaps. Second is that all polynomial functions have only smooth rounded terms, unlike absolute value of x, which looks like a v. Two types of polynomials are either when n is even or n is odd. What I mean by n is the highest power of the polynomial, or also known as the degree. As you can see here, I have Desmos pulled up. Notice it's just a parabola with the vertex at 0. The higher the power gets, the flatter this graph will be around the origin. As you can see with x to the 4th, x to the 6th, x to the 8th, the graph just gets flatter and flatter around the origin. Same happens when the highest power, or the degree of the function, is odd. As you can see here, we have x cubed. X to the 5th is a little flatter around the origin. X to the 7th even more, and x to the 9th is even more. Now let's talk about the leading coefficient test and the end behavior of polynomials. So first let's talk about the two polynomials we just talked about. So f of x is equal to x squared. As mentioned before, all even polynomials act very similar. That is no different for the end behavior of this function. Notice the leading coefficient in f of x equals x squared is 1. And obviously we don't write 1, but we know that it's there. That is a positive leading coefficient for an even function. So let's take a look at the end behavior of this function. Notice as x approaches negative infinity, this function approaches positive infinity. Same happens when x approaches positive infinity. The function x squared also approaches positive infinity. If the leading coefficient was negative, such as negative x squared, the graph would just be an upside down parabola. Now notice that the end behavior is negative infinity and also negative infinity as x approaches positive and negative infinity. This is true for all even functions. Now let's take a look at functions in which the degree of the polynomial is odd. One of those functions would be f of x is equal to x cubed. As one of the parent functions, we are pretty familiar with it, and we know that it looks like this. So as x approaches infinity, the function, notice it goes up in the sky. In other words, the function also approaches infinity. However, as x approaches negative infinity, the function approaches negative infinity as well. Notice here the leading coefficient is positive. In this case, it's positive 1. If the leading coefficient was negative, for example, f of x equals negative x cubed, that function would just be reflected by the x-axis and will look like this. And in this case, as x approaches negative infinity, this function approaches positive infinity. And the exact opposite happens as x approaches positive infinity, this function approaches negative infinity. Take a look at this example and see if you can figure out what the end behavior will do. What will happen to this function on the right side and on the left side? First thing we notice is that this is an even power function. The degree of this function is even. Therefore, it's going to behave just like a parabola. Since the leading coefficient, the number that stands in front of a variable with the degree, is positive, in this case, again, it's 1, we know that it's a regular U-shaped function, or something that's going to behave like a U. In this case, we know that this function will go to positive infinity as x approaches negative infinity, and positive infinity on the right-hand side as x approaches positive infinity. But what happens here in the middle? Let's find out. One of the most important problems in algebra is finding zeros of polynomial functions. Another word for finding zeros is solving for x, trying to find out what is x when the function is equal to 0. Let's take a look at our first example. F of x is equal to negative 2x to the fourth plus 2x squared. The first thing we want to do is set this function equal to 0. Negative 2x to the 4 plus 2x squared is equal to 0. We're trying to solve for x. The first thing you will notice is that 2x squared is common to both of those terms. So I'm going to take it out. I'm not only going to take out the 2x squared though, I'm going to take out negative 2x squared, and I think you'll see why in a second. So if I take out negative 2x squared from the first term, I have x squared left over. If I take out negative 2x squared from positive 2x squared, I have negative 1 left over. Notice this parenthesis here is factorable. So I can write this, or I can break this down a little further into x plus 1 and x minus 1. And you can FOIL to make sure that that is correct. Now that I have this, I can set each one of these parts equal to 0 and solve for x. So negative 2x squared equals 0, x plus 1 equals 0, and x minus 1 equals 0. So if I solve this for x, I will divide both sides by negative 2. X squared equals 0. Take a square root on both sides. And I just have 0 because you don't write plus or minus 0 is just 0. So I know one of my roots is 0. Subtract 1 on both sides. I know my second root is negative 1. And add 1 to both sides. X is equal to 1, which is my third root. Which brings me to introduce you to the following two statements. 1. The function f has at most n real roots. In other words, take a look at the degree of a function, or the highest power. That is the maximum amount of roots a function can have. 2. The graph of a function can have at most n minus 1 turning points. In other words, where the function changes from increasing to decreasing, or vice versa, from decreasing to increasing. So in this case, since n is 4, this function has at most 3 turning points. Let's talk about the graph of this function. The first thing you should notice is that this function's degree, or the highest power, is even. Therefore, it's going to behave like a parabola would. So it's either both positive or both negative. Since it's a negative leading coefficient, this is going to behave like an upside down parabola. In other words, I know that my graph is going to be pointing down on both left and the right side. I also know that the roots are at 0 and negative 1 and at positive 1. This gives us a lot of information about this function. I know that it has to start here and end here. Therefore, I know part of it has to look like this. Between negative 1 and positive 1, it also has to pass through this point, through 0. The only way it's going to do that is if it makes a turn at 0 and doesn't actually go through it, because that would give you another x-intercept. And this is just a rough sketch of what this graph would look like. The last topic I wanted to mention was the Intermediate Value Theorem. What the Intermediate Value Theorem basically says is that if you plug in some random points x and y, or maybe not so random, and your results go from negative to positive or positive to negative, it implies that there is a root in between those two x points. For example, f of x is equal to x cubed minus x squared plus 1. And so we don't have a graphing utility to figure out where my root is located. I can plug in some random points x and find out what the value of that function is at those points. So I'm going to plug in -2, -1, 0, and +1. When I plug in those numbers for x, I have -11 as my result, -1, 1, and 1. Notice how the function f of x, or the value of the function f of x, also known as the y-coordinate, changes from -1 to +1. This implies that there has to be a root in between -1 and 0. That is when you can dive in a little deeper and plug in points like -0.1, -0.2, -0.3, and so on, where exactly the value of 0 occurs. I hope you found these examples helpful. Be sure to like and subscribe, and I hope to see you next time. Take care.